Okay, chapter 14 of Pure Year 1, Exponentials and Logarithms. This is a pretty new chapter and you won't have seen a lot of this before. The only thing that you may have seen from higher GCSE is potentially exponential graphs. So we're going to start off by looking at exponential graphs, and these are just two examples. E is just a number, so it's a number, it's a special number though. It's about 2.71. Okay, it's a special case, a special number that we're going to be introduced to, that we're going to be using, but it's another, here it's used as another exponential graph. Exponentials are used effectively to give us models to understand the world, and especially to understand growth. Growth of things like population is a good example, whether that's increasing exponentially or whether we have something like exponential decay. Half-life is an example of that for one. E, we are going to then look at how to differentiate E. So you need to make sure you've done chapter 12 before this. And because we're doing all this work on exponentials at the start, then we're going to look at the other side of it. So the inverse of exponentials are logarithms, which we often call logs. And there are laws, as there are laws for indices, there are laws for logs. Finally, we look at using logarithms. One of the uses of this is in modeling and for us to sort of easily understand situations. So to begin with, you could always use your calculator if you get lost to make a table of values. So make sure you know how to do a table of values with your class whiz. And if you did this, well, 2 to the power of -2, that's the same as putting it in the denominator, so 1/2, but 1/2 squared. So it's a quarter. So that would be a quarter. That would be a half. Anything to the power of 0 is 1. And then what we notice is that we're multiplying by 2 effectively for every step here. It starts to grow quicker and quicker and quicker because it's not adding on the same each time. It's multiplying by the same amount each step. So this is the graph of an exponential. A couple of interesting properties. First of all, notice that it never occupies negative y space here, because you can't raise something to a power and get a negative answer. So it's always above the x-axis. There is an asymptote here, though. So the asymptote would be, y equals 0. It will get very close to that line, but it won't quite get there. Yeah, and this is the sort of shape that we would expect. So very useful in modeling situations. If we compare a few, so what's the difference here? These are all exponential graphs. They're exponential because the x is in the power, yeah? You could use a table of values to have a look at this, and you'll notice some interesting things when you plot them all together. So because you're multiplying by the same amount for each step of x with these, it means that green, because it has the highest base, will grow the fastest on the right-hand side, because you're multiplying by 3, so it would be like 1 and 3 and 9 and 27, whereas 2 is 1, 2, 4, 8, so it's a bit slower. 1.5 will be slower again, 1.5, 2.25. Yeah, it doesn't grow quite as quickly. The other side of that, though, is on the left-hand side. If you're going to the left, instead of multiplying, it's a bit like you're dividing by that number. So you'll notice 3 to the x goes down quite quickly on the left-hand side. That's because it's 1, a third, a ninth, and so on. Whereas if you have 2, a half, a quarter, an eighth, isn't quite as dramatic as that. They all go through 1, though. 1 is an intercept. Why? Because when you do any of these numbers to the power of 0, you're going to get a y value of just 1. Have a go at this one here. So quickly pause, try it with a table of values on your calculator, because there's something quite interesting about this one. So see what you notice. So I'm assuming that you've done that. And if you do this, well, 2 to the x, we've already drawn that one. The blue one we've seen before, okay? The red one, though, you might notice it's going sort of the other way round. In fact, it seems as though we have a reflection across the y-axis. So why is this? Well, this is because you could write a half as 2 to the -1, but still to the power of x. So this is the same as 2 to the -x. If you remember transformations of graphs from chapter 4, that kind of explains the shape that we have. So as a shortcut, if the base is less than 1, you will actually have a decaying graph because you'll be multiplying by a fraction each time as you go to the right. So it will go down and down and down. So what we have then is 2 to the x is exponential growth. A half to the x, which is the same as 2 to the minus x, is exponentially decaying. And in general, we should be able to recognize, anything here to the power of x or to the power of minus x, and we should be able to draw these. Again, they both go through 1, don't they? So a couple of other examples. What can we do? Well, we can mix graph transformations in, as we just said. So we know that this is a 2 to the x graph. What's the impact of the +3? Well, it's inside the function. You could put brackets here if you like. It's inside the function and you're adding, so it's a translation, and it has the opposite effect that you might expect in the x direction. So this will actually go to the left. Now, you can't really draw that much that's very interesting. I mean, I would still draw the asymptote. I would still say y equals 0 asymptote. But the main thing to mark would be this point here. So put x equals 0 in and see what you get. Well, if you put x equals 0 in, 0 plus 3 is 3, to the power 3 is 8. So whereas before it went through at 1, it will go through now at 8. So pause here and have a quick go at the one underneath. So remember, this is a number less than 1 for the base. So you need to take that into account when you're drawing it. And also consider inside or outside the function for the transformation element in the power. Okay, so it should look something like this. They haven't drawn very much of this axis part here. So 0 minus 3 is minus 3. Okay, and a half to the power of minus 3, well, the minus turns it upside down, and to the power of 3, it becomes 8. So that's the key part there, and the shape is really, really important with the fact that it doesn't cross the x-axis. That's what we're looking for. So just to sort of reveal a little bit neater for the first one as well, okay, this is what we would be going for. And that takes you up to 14a then. So we need to recognize the shape of these graphs, but also be able to transform them in various ways. Recommended questions for you to have a go at, and some hints for the questions in 14a. These would be very good questions to make sure that you have a good go at.